Hello student, let's go to today's material. Type my name. First search result, then click teaching, and then introductory mathematics for economists. Now let's go to class folder, and then class O2, linear algebra. You can download this file as a PDF format. It is downloading. Then open with a PDF program. Yes, like this. So today's topic is linear algebra. I have a recommendation. First, students should watch all videos at this link, Essence of Linear Algebra. You can simply click this link. Yes. There are about 15 videos. They are all highly good. Let's take a look at the very first one together, just for test. Yeah, this is the advertisement.
달에 사는 토끼는
Skip advertisement. So this is the start.
Hey everyone! So I'm pretty excited about the next sequence of videos that I'm doing. They'll be about linear algebra, which, as a lot of you know, is one of those subjects that's required knowledge for just about any technical discipline. But it's also, I've noticed, generally poorly understood by students taking it for the first time. A student might go through a class and learn how to compute lots of things, like matrix multiplication, or the determinant, or cross products, which use the determinant, or eigenvalues. But they might come out without really understanding why matrix multiplication is defined the way that it is, why the cross product has anything to do with the determinant, or what an eigenvalue really represents. Oftentimes, students end up well practiced in the numerical operations of matrices, but are only vaguely aware of the geometric intuitions underlying it all. But there's a fundamental difference between understanding linear algebra on a numeric level and understanding it on a geometric level. Each has its place, but roughly speaking, the geometric understanding is what lets you judge what tools to use to solve specific problems, feel why they work, and know how to interpret the results. And the numeric understanding is what lets you actually carry through the application of those tools. Now, if you learn linear algebra without getting a solid foundation in that geometric understanding, the problems can go unnoticed for a while until you've gone deeper into whatever field you happen to pursue, whether that's computer science, engineering, statistics, economics, or even math itself. Once you're in a class, or a job for that matter, that assumes fluency with linear algebra, the way that your professors or your coworkers apply that field could seem like utter magic. They'll very quickly know what the right tool to use is, and what the answer roughly looks like, in a way that would seem like computational wizardry if you assume that they're actually crunching all the numbers in their head. Here, as an analogy, imagine that when you first learned about the sine function in trigonometry, you were shown this infinite polynomial. This, by the way, is how your calculator evaluates the sine function. For homework, you might be asked to practice computing approximations of the sine function by plugging in various numbers to the formula and cutting it off at a reasonable point. And in fairness, let's say you had a vague idea that this was supposed to be related to triangles, but exactly how had never really been clear and was just not the focus of the course. Later on, if you took a physics course, where sines and cosines are thrown around left and right, and people are able to tell pretty immediately how to apply them and roughly what the sign of a certain value will be, it would be pretty intimidating, wouldn't it? It would make it seem like the only people who are cut out for physics are those with computers for brains, and you would feel unduly slow or dumb for taking so long on each problem. It's not that different with linear algebra, and luckily, just as with trigonometry, there are a handful of intuitions, visual intuitions, underlying much of the subject. And unlike the trig example, the connection between the computation and these visual intuitions is typically pretty straightforward. And when you digest these and really understand the relationship between the geometry and the numbers, the details of the subject, as well as how it's used in practice, start to feel a lot more reasonable. In fairness, most professors do make an effort to convey that geometric understanding. The sine example is a little extreme. But I do think that a lot of courses have students spending a disproportionate amount of time on the numerical side of things, especially given that in this day and age, we almost always get computers to handle that half, while in practice, humans worry about the conceptual half. So this brings me to the upcoming videos. The goal is to create a short, binge-watchable series animating those intuitions from the basics of vectors up through the core topics that make up the essence of linear algebra. I'll put out one video per day for the next 5 days, then after that put out a new chapter every 1 to 2 weeks. I think it should go without saying that you cannot learn a full subject with a short series of videos, and that's just not the goal here. But what you can do, especially with this subject, is lay down all the right intuitions so the learning that you do moving forward is as productive and fruitful as it can be. I also hope this can be a resource for educators who are teaching courses that assume fluency with linear algebra, giving them a place to direct students that need a quick brush up. I'll do what I can to keep things well paced throughout, but it's hard to simultaneously account for different people's different backgrounds and levels of comfort, so I do encourage you to readily pause and ponder if you feel that it's necessary. Actually, I'd give that same advice for watching any math video, even if it doesn't feel too quick, since the thinking that you do on your own time is where all the learning really happens, don't you think? So, with that as an introduction, I'll see you next video.
Okay, so I want every student to watch all videos at this link again. These 15 videos. In addition, if the link above, this is too hard, or you want to study more technicalities of linear algebra, I recommend students to watch videos at this link, Khan Academy, Linear Algebra. Here, linear algebra, and there are many classes. For example, let's click this linear combination space spans, and there are many, some more videos. So again, this is also very good materials. So if you want to study linear algebra in more technical level, or you can study this part. Let me explain matrix. In mathematics, a matrix or plural matrices is a rectangular array of numbers, symbols, or expressions arranged in row. Row is this way, and columns this way. This matrix, for example, is 2 by 3 matrix because it's a 2 row and 3 columns in this way. Okay. The individual item in an m by n matrix A, in which there is m rows and n columns. The individual item is denoted by A, ij, small ij, where max I equals m, of course, because there is only m number of rows, and max of j is n, because there are n number of columns. They are called the element or entries of matrix. So this one is m by n matrix. The entry aij, this is change in j, this is change in I. The m rows are horizontal and the n columns are vertical. Next. This one is row vector, means 1 by n matrix. For example, 3, 7, 2. Column vector is the default. Actually, when we say vector, default is column vector. Column vector is n by 1 matrix. A matrix with only one column, sometimes used to represent a vector. Square matrix is n by n. The number of rows and number of columns are the same. A matrix with the same number of rows and columns sometimes used to represent a linear transformation from a vector space to itself, such as reflection, rotation, or shearing. Covariance matrix is an important kind of matrix. In probability theory and statistics, a covariance matrix, also known as dispersion matrix or variance covariance matrix, is a matrix whose elements in the ij position is the covariance between i's and j's element of a random vector. A random vector is a random variable with multiple dimensions. So, for example, throughout this article, bold-faced unsubscripted x and y are used to refer to random vectors, and unbold-faced subscripted xi, xj, and yi are used to refer to random scalars. Scalars means just one by one matrix or just number constant, not a matrix, scalar. If the entries in the column vector, here is x equal x1 to xn, this is column vector, are random variable. The entry each x1 to xn, if they are random variable, each with finite variance, if it is infinite, we cannot define variance, therefore we cannot define variance matrix. Anyway, each random variable x1 to xn, they have finite variance, then the covariance matrix, in this case sigma. Covariance matrix is the matrix, it is the matrix, and whose i's row and j's entry is the covariance in this way. So this entry sigma ij is covariance between xi, i's x and j's x. So covariance xi xj. Of course, the definition of covariance is exponential, expectation of xi minus expectation of xi, yj minus expectation of xj minus expectation of xj, which is same to expectation of xi xj minus mu I mu j. Here mu I mu j are expected values of xi xj respectively, where mu I we will read this as mu I equal exi. This is the expected value of i's entry in the variance x. In other words, the covariance matrix looks like this. It is square matrix from x1 mu1 x1 mu1. So this is basic variance. So these diagonal terms are all variance, and up diagonal terms are all covariance. Now the inverse of this covariance matrix, if it exists, is the inverse covariance matrix, also known as concentration matrix or precision matrix. This covariance matrix is particularly important in statistics and finance. In finance, covariance matrix is very, very important. We will learn how to use covariance matrix in finance later. Next, I recommend the students to read the article in this link. Let's click. Here, properties of covariance matrix. So, yeah, this is very useful. For example, this is a covariance matrix. It is comparable to covariance. We know we have two ways to find covariance, to calculate covariance. And this is positive semi and symmetric. Positive semi-definite. It means, roughly means, this matrix is some sort of positive value. Variance is always positive. So variance covariance matrix or covariance matrix should be some sort of positivity. Should have some sort of positivity. In the symmetric, it means that entry in ij is the same to entry ji. It is natural because covariance between xi and xj should be same to covariance between xj and xi. Now this one, variance of ax plus a. Then it is a variance x, a transpose. This means transpose. Now covariance xy equals covariance yx transpose. And you can read others. And this is another introduction, Bloom matrix. Yeah, the joint mean and the joint covariance about xy can be written in block form this way. Yeah, this is also interesting. R is useful to deal with matrices. So let's click this one, matrices. Here, it explains how to use R to generate matrices, for example. So for example, let's try this one. Let me start R. R. So for example, in the web page, this one, let's copy and paste this one. Let's copy and paste this one. This one, yes. And if we type M that, it shows matrix. So let me show you step by step. First, M dot is the matrix, and then we have parentheses, and C means, yes, it is the arrays 1, 2, 3, and 11, 12, 13. Okay, so we are gonna make a matrix whose entry, the entry of the matrix is 1, 2, 3, 11, 12, 13. And then let's say number of row is 2 and number of columns is 3. Then we have something like this, M that. Okay. Or if you want to take a look at matrix directly, then it is like this. Alternatively, if you type this one again, 1, 2, 3, and let's make it 3 by 2. 3 row and 2 column, then apparently it has 1, 2, 3 now, and then 11, 12, 13 this way. So it fills this one first and this one later. Okay. Now let's go to the previous case. In this case, it shows the entries, and where n row equals 2, n column is 3. N row means number of row. Actually, you don't have to write n row equals this part. In my example, I didn't write anything. N row equals 3, but I didn't write it down. It is fine. And by row, default is by row. So in this case, we arrange this one by row. In this case, it is defaulted by column. So in this case, it is 1, 2, 3, 11, 12, 13. So if I change this one by row, true, by row true, then remember, now it is row first, 1, 2, 3, 11, 12, 13. Now the order is different. It is 1, 2, 3, 11, 12, 13. So if we don't have this part by row equal true, the default is column. It fills column first. And if we write this one, it fills row, the decimal row. And then there is a way to give a name of the dimensions. So here, it is the row 1, row 2, it is name of the row, and C1, C2, C3, they are row of the column. So let me copy and paste this one, and then type M that, and look at this. We have name for rows and then name for column, right? So dim names equals list of 2 lists. First list is row names, second is column name. So this is one useful way of writing down matrix in R. Let me show you another example. In R, if you write 1 colon 10, it generates something like this. Okay, it generates number from 1 to 10. Now let's make a matrix. Now 1 to 10, and then number of row is, let's say, 2. Number of column is 5. Then it should have something like this. And then if you want to fill this matrix by row, then by row true. Then look at this. Now it fill by row first. Okay, so So R is very convenient. Okay, R is very convenient. For matrix algebra with R, you can check this link. So let me copy and paste this link. Actually, I can simply click this one. Yes. Then quick R. Now it shows matrix algebra. AB, element-wise multiplication. Let me show you. So first, let's write down A as a matrix, C. Okay, let's write down M that A equals M that we just defined, and let's define P as the matrix 1, 2, 6, 2 rows, 3 columns. Yes, B. Okay. Now, if I do A multiplied by B, then it is element by element multiplication. 1, 1, 1, 2, 3, 6, 3, 5, 15, something like this. So, A multiplied by B is element-wise multiplication. Now, A percent star percent B is matrix multiplication. So, clearly, if I do A B, it shouldn't work because in matrix multiplication, number of row and number of columns should be same when you multiply each other. So instead this one, this is transpose of B. So if I multiply transpose of B, now it should work. Right? Transpose of B was 3 by 2 matrix, A is 2 by 3 matrix. So A multiplication transpose of B should work. And this is outer product. So let's say A, and then in this case actually we can do T A, and then B. There is outer product. Yeah. Now it is now you can do the cross product, A B cross product. So if you do cross product A and B, it looks like this one. Sorry, cross product A B, something like this. So A again, B looks like this, right? And then this is basically same to transpose A and B. So transpose of A multiplied by B is this one, which is same to cross product AB. Okay, they are same. Cross product A, it is the A prime A. It's A prime A. So cross product A is cross product A and itself A. TA, as I explained, transpose, and diag X. It creates a diagonal matrix with element X. For example, diag C1, 2, 3. Then it is the diagonal matrix with the diagonal term is 1, 2, 3. Okay, looks like this. Likewise, diag 1 to 10, and it is the 10 by 10 matrix with diagonal terms is from 1 to 10. Now, diagonal of A. Now, when A is metric, it returns a vector containing the element of the principal diagonal. Okay, so for example, cross product of A, B looks like this. So principal diagonal term is 23, 54, 93. So let's try diag of this one is indeed 23, 54, 93, 24, 54, 93. Okay. Now solve AB. Okay, so diagonal K, so if K is square, it creates K by K identity matrix. So identity matrix. So for example, diag 3 Well, it becomes 3 by 3 identity matrix. So yeah, likewise diag 2 is 2 by 2 identity matrix. Yeah, identity matrix I. And then another into solve. Solve A, B. Returns the vector x in the equation b equal ax. So it is basically useful to calculate systems of linear equations. So it is same to this return is same to b equal ax, such that this x should be x is, as you see, a inverse b. This is so if you do this one, it returns a inverse b. A inverse. Solve A, it returns inverse matrix. So for example, 2 multiplied by diagonal 2, 2 by 2, so you 2 by 2 matrix with diagonal 2. Inverse matrix of this one is solve 2 diag 2. Yes, it is half. So this one is inverse matrix of this one. So let's try this one. Is 2 multiplied by diag 2. Then it's the identity matrix. Solve. And then we have other useful techniques like eigenvalue. We will learn other things shortly. Well, this is actually useful. C bind AB. It's combined matrix horizontally. Return a matrix. For example, 1 to 10, 2 to 11. Okay, so if I do C bind, column bind of 1 to 10 and 2 to 11, it becomes like this. Column bind 1 to 10 and 2 to 11. How about row bind? Okay, if I do row bind, R bind, that is 1 to 10, 2 to 11. Okay, so it is a column bind and row bind. This is row mean and row sums. So for example, let's see, let's take a look at A matrix. So let's see row sum A. Row sums A, then it generates sums of row. So sum by the row. So 1 plus 2 plus 3 is 6, 11 plus 12 plus 13 is 36. Likewise, we can do call sum. This is column sum. So this one, sum of this one is 12, sum of this is 14, sum of this is 16. Column sum. And then you calculate row mean. This is average, and this column mean is average. Okay, so row means instead of this one, you can do call means. Right? It generates average of these two. Average between this one. So at the column level, so average of these two is 6. Average 7, average A. How about row means? Of course, then it generates by the average by the row. Average of these 3 is 2, average is 12, so 2, 12. This is very convenient, isn't it? Let's go with this one again. So for matrix algebra with R, check this link that I just discussed. Now, linear combination. One important concept in matrix or linear algebra is linear combination. What is the definition of linear combination? Definition: given a set of vectors, you can regard this vector as column vectors. That's more useful. So, given a set of vectors from V1 to Vk, so we have a k number of vectors in a vector space V. Okay, any vector of the form V, which is A1, V1, A2, V2 here, those A. For some scalars A1 to AK, they are just numbers. So basically, it is kind of weighted average of from V1 to Vk. And this one, using scalar, and this one is called the linear combination of V1, V2, and Vk. Again, given a set of vectors and some scalars, if we calculate this one, it is sum product basically. It's called sum product. This is sum product is called the linear combination of V1 to Vk. So for example, let's say V1 is 1, 2, 3 vector. Vector V2 is 1, 0, 2. Now you can express u minus 1, 2, minus 1 as a linear combination of V1 and V2. Then we must find the scalar A1, A2 such that u equal A1, V1. So if we write, so this one multiplied by A1, this one multiplied by V2, and sum them all, then minus 1 should be equal to A1 plus A2, right? This one 1, 2, 3 is same to this one, and this one 1, 0, 2 is this part. So this and this should be this one, same to this one. Now, given a set of vectors V1, V2, Vk in a vector space V, about vector space, you can check the YouTube link I introduced. Anyway, given a set of vectors V1, V2, Vk in a vector space V, the set of all vectors which are linear combination of V1, V2, Vk is called the span of V1, V2, Vk. In other words, i.e., span of space, basically we are spanning a space, span of set of vectors V1, V2, Vk is basically vector in vector space such that V is some sort of combination of those things. Okay, so all set of all parcel V is called the span of those set of vectors. Now, given a set of vectors S, V1 to Vk in a vector space V, S is said to be span V. If span S equals to original space V. Now, given a set of vectors V1, V2, Vk in a vector space, then they are said to be linearly independent. If the equation has only trivial solution, which means that when we have this equation and we want to find the solution, this one, it means we want to find the C1 to Ck, the only solution that satisfies this one is CR all 0. Of course, CR all 0, then it is 0. And if that 0, and they are called trivial solution because when those C are 0, it is trivially 0. So this 0, 0, 0, K0, K number of 0 are called trivial solution. And if we can make this one equals 0 only with trivial solution, then it is called linearly independent. If V1, V2, Vk are not linearly independent, they are called linearly dependent. So, intuitively speaking, if a vector is in the span of those things, those vectors, it is linearly dependent. If another vector is not spanned by this one, is linearly independent. Note, V1, V2, Vk is linearly dependent if and only if some Vi can be expressed as a linear combination of rest. That's why we call it dependent. So for example, if we express one of those vectors with others, then it is linearly dependent. If it is not possible, it is linearly independent. For example, suppose there is a non-trivial solution, and if we divide each side with the C1 and move this part here, then we are basically expressing V1 with a combination of other vectors from V to Vk. In this case, if it is possible, it is called linearly dependent. Now, the matrix associated with stretch by a factor k along the x-axis is given by K001. Okay, so actually we can click this link. Okay, So this matrix is called stretching. Stretching in the direction of x. And this matrix is stretching in the direction of y. The matrix also is stretched by a factor k along the x-axis. So similarly, a stretched by a factor k along the y-axis the form of x prime is x and y prime ky. So we have x is the same, but y is increased by k. So we are stretching vector into the k direction. So it is stretching direction of y. Likewise, it is x prime in this case. X prime is kx and y prime is y. So with this method, we are basically stretching the space in the x-axis. Now another interesting one is rotation. This one is rotation matrix. Okay. So let me explain. So suppose this is a point xy, and maybe we want to rotate by theta, and then we will have another vector y prime. So we are basically rotating a vector, and then the relationship between this first one and the second one, x, y, and x prime, y prime, is basically this one. So x prime, y prime is cosine theta minus sine theta, cosine theta, and xy. In fact, it is not so difficult to prove. So let me show you. So for simplicity, first let me think about very easy one. Suppose this one. Let's say this is 1 or 0, and then let's rotate this one by theta. Then what should be the point of this one? Then of course the x is because the length of this one is 1, because this is 1, okay? This is 1. So the x-axis, this one dew point, is the cosine theta. And the height of this one, because this is 1, the height of this one is sine theta, right? Sine theta. So if we do the rotation of 1, 0, then it becomes cosine theta and sine theta, right? And then let's think about 1, 0, and now let's remove this one, and remove this one, and again let's think about this line. Okay, let's make it thicker. Okay, so this is the point of 0, 1, and then if we do the rotation by theta, then we will have another one. Then let's think about what is the coordinate of this one. So this height, because this is theta, this height is straightforward. This height is sine. So this height is sine theta. And this one, this line is of course, this is a theta. Okay, this is theta. So this is the 2 pi minus theta, right? Alternatively, actually, what you can do is, yes, actually, let me do it again. Let's delete this one, and let's delete this one, because I want to write it bigger. So straight line, and then straight line, okay, and then this one is 0.1, and then I do the rotation this way, okay, rotation this way, and then let's say this is the theta, then I am interested in this point first. The length of this side, so the length of this side, its length of this side is same to this one. Okay, so this is the basically sine of this one. So this one, okay. So basically, the length of this one is same to this one, sine. So this is sine theta, but it is minus side, so we should minus over here, minus sine theta. How about height? Height is the, now we can think about this cosine of this line. So yellow, this is same to this one. So this height is basically cosine of theta. So the point of this one is minus sine theta and cosine theta, right? So this one becomes minus sine theta, cosine theta. So you wanna think about the matrix A, B, C, D, such that if you apply 1, 0, then it becomes cosine theta and sine theta, right? If you multiply 1, 0, basically it picks only the first line. Therefore, what you can do is basically, if we move this part, cosine, okay, paste, and then this part should be over here. Now instead of this one, now if we multiply now 0, 1, okay, 0, 1, now the answer is, in this case, the answer is now here minus sine theta and cosine theta, and then this one, this 0, 1. Now this one fixed because I multiply 0, 1. Now it fixes only this one, so this part should be equal to this one. So I can just copy and paste this part over here, right? So I can select this part, paste, and I can move this part over here. Okay, and this is the over here, where it is slightly so this one, right? This part. So now we got the rotation matrix, and this is same to this one, rotation matrix. So for rotation by angle theta counterclockwise about the origin of the function, then x prime is x sine theta minus y sine theta, and y prime is x sine theta, y cosine theta, which looks like this one. Similar, a rotation clockwise. Now it is clockwise. So basically we are moving this way, so moving this way counterclockwise. Then it is basically counterclockwise, so it is minus theta. So in this rotation matrix, I can only put minus sign in the rotation matrix. Cosine minus theta and minus sine theta. Minus theta, because it is clockwise, it is minus, so it is a sine minus theta and cosine minus theta, right? This way. And as you know, cosine minus theta is the same to cosine theta. So we can delete this one. Cosine theta is minus sine theta. So we can this part delete this one. And then minus sine minus theta is minus sine theta, right? So which means we put minus over here, and then actually we delete this part. Likewise, we delete this part and minus minus plus. So it is rotation matrix the clockwise. So only difference is we have minus over here, in the counterclockwise minus over here. So we have this. Now shearing is like a slanting, visually slanting. Well, then the matrix looks like this one. For more information, you can do the shear mapping. Shear mapping this way. Mapping. We have also reflection and orthogonal projection. You don't have to. Well, orthogonal projection and reflection, they are both important, but at this point you don't have to know this one. So, but you need to know stretching, rotation, and shearing. Rotation. Thank you.